Chemical Bonding, Lecture 1. No doubt you've studied bonding before, but you're going to get a little bit more of it again. And in this, we're going to talk about ionic bonds, covalent bonds, Lewis structures, resonance hybrids, formal charge, octet exceptions, and polar bonds. But let's start out by talking about what bonding is. You probably think of bonding as a way of holding atoms together or ions together, and that it's attractive forces. And you're largely correct, but I want you to understand that bonding is actually located somewhere on a continuum. For example, we may talk about things being ionically bonded, or we may talk about things being covalently bonded, and we think about them being opposites, if you will. But actually, there's a continuum that exists between ionic and covalent. And on that continuum lies polar covalent, something that's covalent but not purely covalent, or it's kind of ionic but not completely ionic. Well, bonding is by degrees. Now, whether the bonds are ionic or covalent or polar covalent really depends on the attraction that atoms have for the electrons that are in the bond. And that attraction that atoms have for electrons in the bond is called electronegativity. Over here in the area of ionic bonds, we will have a very large difference in the electronegativity between two particles. We will have a moderate difference in the polar covalent bonds, or we may have the same or a small difference in the purely covalent bonds. And later on, we will talk about the case of covalent bonds occurring when there is no net dipole moment. But that's a conversation for a little later in this unit. Here's a table of electronegativities that we need to look at. Now on here I have put the major elements that you're going to be talking about. Well, I've put just about everything but the inner transitions. And I want you to notice electronegativity changes in what direction? Well, it increases as we go up and as we go across. So as we start with lithium and go to beryllium and boron, carbon, nitrogen, oxygen, and fluorine, it goes up. The same thing happens on any period. Or as we go up the periodic table, for example, from astatine to iodine to bromine to chlorine to fluorine, it goes up. So therefore, looking at it this way, the most electronegative element should be fluorine, and it is. And the least electronegative should be francium. Now you say, well, francium and cesium have the same. Well, we probably don't have enough of francium and haven't experimented with it enough to know with certainty. This is an estimated electronegativity. But we can say that it lies in this area. When we talk about ionic bonds, we're thinking about those bonds that are formed when opposites attract, when ions of opposite charges are attracted to each other. Cations with positive charges and anions with negative charges. But let's look at it from an electronegativity standpoint. And our rule of thumb says that if we have a difference in electronegativity values of 1.7 or greater between two elements, or between two atoms, in this case it would be between two ions, it will indicate the bond is predominantly ionic. So look it up on the table if you're ever uncertain. And if you see an electronegativity difference of greater than 1.7, assume that the bond formed between those two particular elements is ionic. Now technically there's not a molecule. Instead, in the solid state, we have an ionic lattice arrangement. When do we have molecules of these things? Well, perhaps in the gaseous state, but we're not going to deal with that right now. Let's look at the ionic lattice arrangement. Particularly, let's look at the arrangement of sodium ions and chloride ions in solid sodium chloride. And here they are. Now I want you to notice that chloride ions are surrounded by the positive sodium ions, and sodium ions are surrounded by the negative chloride ions. And you'll have to use your imagination and see this in 3 dimensions. Look at the way the forces are exerted. Chloride ions exert their negative charges in all, or their negative attraction, if you will, in all directions. Sodium ions exert their force equally in all directions. That's important. So that a sodium ion is not particularly separating out a chloride ion and saying, hey, that's the other part of my compound. No, no. It is a lattice arrangement. Now, there are some important characteristics of ionic bonds. First of all, ionic bonds are non-directional. In other words, they don't lie in a specific direction. Or you may think of them as being omnidirectional if you wish. But those forces of attraction are exerted equally in all directions. Ionic bonds are characterized by having high lattice energy. We'll get to that in just a moment. And not only do they have high lattice energy, they have high melting points, very high melting points. Let's look at lattice energy. Now, lattice energy is the energy that's needed to separate a mole of an ionic material into its gaseous ions. For example, if we had sodium chloride solid and we heated it, it would form sodium ions and chloride ions in the gaseous state. And you might think of it as a way to measure the strength of ionic bonds. The stronger those ionic bonds, the stronger they are, the more energy it's going to take to split those ions off from each other, or off from other ions, get them out of that lattice work and into the gaseous ion state. And what is lattice energy related to? Well, it's related to the size of the ions and the magnitude of the charge on those ions. Let's start with size of ions. As the ionic radius increases, the lattice energy decreases. Why? Stop for a minute and think about it. If you increase the ionic radius, why would the lattice energy decrease? Does it have to do with the distance between the nucleus of that ion and the position or the distance of those outer electrons? Well, let's look at this. If we look at the NaX compounds, in other words, sodium chloride, bromide, iodide, and fluoride, and we list them out, here they are. Now, we've listed them from the smallest to the largest. The ionic radius increases in what direction? Well, sodium's the same in all of them. So it's going to have to do with the difference in the anions. And you're going to find that the ionic radius increases in this direction. If the ionic radius increases from sodium fluoride all the way up to sodium iodide, then what happens to the lattice energy? And the answer is the lattice energy decreases. The energy required to separate those compounds into their gaseous ions decreases. Okay, so the lattice energy for sodium fluoride is higher than the lattice energy for sodium chloride. That means it takes more energy to separate the sodium fluoride into its gaseous ions than it does sodium chloride. Does it make sense to you when you think about ionic radius? One way to look at lattice energy is to look at melting points. We know that there is a correspondence between lattice energy and melting points. So let's look at the melting points of those NaX compounds. Here they are. Now, how do the melting points go? Well, let's see. We know the lattice energy and melting points correspond. Yeah. So the melting points increase in this direction. That means sodium fluoride has a much higher melting point than sodium iodide. That's right. Does it make sense to you? The lattice energy of sodium fluoride is much higher than the lattice energy of sodium iodide. Why? Think about how closely the ions may pack together. The sodium fluoride, very small. The sodium iodide, the iodide is very large. The ions can't get together as closely when you're dealing with sodium bonded to iodine as they can when you're dealing with sodium bonded to fluorine. Now let's look at magnitude of charge. And I will tell you that as magnitude of charge increases, the lattice energy increases also. So as the magnitude of charge goes, so goes the lattice energy, or whichever way you want to say it. Let's look at the lattice energy and melting points for a series of chlorides. Here we have ferric chloride, calcium chloride, and potassium chloride. The ferric ion, or the iron 3, is a +3. The calcium is a +2. The potassium is a +1. Our charge is increasing in this direction. And of course, I'm talking about the charge of the cation. So let's look at lattice energy. Lattice energy increases in this direction. The charge is bigger. The force of attraction that is exerted is larger. Melting points? Melting points also increase. So the melting point of ferric chloride is larger than the melting point of calcium chloride, is larger than the melting point of potassium chloride. Think about it. As lattice energy increases, the melting point is going to increase, and it's logical. Now, in summary, if you increase the size of the ions, you decrease the lattice energy, and you decrease the melting points. If you increase the ionic charge, you increase the lattice energy and you increase the melting points. Now sit down and think about that and get it straight. Let's talk about an easy way to predict ionic bonding. You're probably not going to have a table of electronegativities with you all the time, but you probably will have a periodic table. So let's look at this. If you have one of these elements, atoms of one of these elements, the 1A's, the 2A's, virtually any of the B's except maybe 2B, bonded with nitrogen, oxygen, fluorine, chlorine, bromine, Naufgelber, or with a polyatomic anion, one of those negative anions, odds are you've got ionic bonding. Otherwise, you can expect the bonding to be a different form. All right, let's go on and look at some of the other forms. Now, we said we were going to cover ionic bonds and covalent and all that. Well, we've covered ionic. But now we need to know that as we look at these others, we're going to be using something that is called the Localized Electron Bonding Model. This is a model to describe how bonding may occur that we call covalent bonds or things of this type. So we're going to talk about localized electron bonding models, LE models. Now when we talk about this, the premise is that atoms are bound by sharing pairs of electrons. Okay. And we also feel that electrons in the pair are located either with a particular atom or in the space between two atoms. Now folks, this is our model. And this is a relatively simplistic model, but it's going to work for us for what we want to do for right now. And we're going to use this concept as we talk about covalent bonding, Lewis structures, the VSEPR theory, and molecular orbital theory. All right, let's go. Covalent bonds. You know this as the bond formed by the sharing of a pair of electrons. Okay, that's good for our model. And we have three types of covalent bonds. We have the nonpolar covalent, which we think is equal sharing between two atoms. We have the polar covalent, which is unequal sharing. Remember, that lies further over on that continuum. And then we have the coordinate covalent, which is the sharing of a lone pair, both electrons being provided by the same atom. A lone pair. And we'll point out some lone pairs as we go. Characteristics of covalent bonds. Well, covalent bonds, we think, lie between two nuclei. They lie specifically between two specific nuclei. They are directional. In other words, they are between those two atoms, not out in all other directions in space. And they may be multiple, yeah. They're formed by the overlap of atomic orbitals. Let me show you. Let's look at hydrogen. Now, here are two hydrogen atoms. The two hydrogen atoms have the nucleus with one proton in each, and they have one electrons in the 1s. Suppose these two atoms were to collide and overlap. The area of the bonding is noted by the darker blue color or the deeper blue color, and that is an area that lies between the two nuclei, and that is where the electrons are expected to be a preponderance of the time, not total all the time, but a preponderance. Bond length is the average distance between two nuclei, and those bonds are going to compress and stretch. It's not static. For example, let's look at hydrogen and see how it behaves. This equilibrium distance is considered to be the bond length. And for this molecule, it's right here, the bond length. Let's look at factors regarding bond strength. Now, bond strength is the energy needed. You can think of it as the energy needed to break a bond, but you do need to realize it's also the energy that may be evolved when a bond is formed. Let's look at some. Consider these three structures. We have a carbon single bonded to a carbon double bonded to a carbon, and a carbon triple bonded to a carbon. Now look at the bond strength of the carbon-carbon single bond, 348 kilojoules per mole. And look at the one that's the carbon double bonded to a carbon, 614 kilojoules per mole. Folks, it's not twice as strong. It's a lot stronger, but not twice as strong. And the same thing occurs with a carbon triple bonded to another carbon. It's not 3 times as strong as a single bond, but it is significantly stronger. So think of it this way. Multiple bonds are stronger than single bonds, but not multiples of the strength. Now we need to take up Lewis structures. Because we need an accounting method for our electrons. And this accounting method is going to be very important because it's going to allow us to study electron distributions of our model, as well as the redistribution of charges that may occur during the process of a reaction. Well, we're going to look at a series of steps that allow us to produce reasonable Lewis structures. Are you ready? Here are the rules. First, determine the central atom. Now, that's really kind of easy. It's generally the one of which you have the least number. For example, with NO3 negative, the central atom is nitrogen. In water, the central atom is oxygen. And the I3 ion, or the I3 molecule, think of it as being like this. And I2. So the central atom is an iodine. Yeah. Then the next thing you do is determine the total number of electrons to be distributed. How do you do this? You do it this way. You add the valence electrons for all of the atoms. So you go through and you figure up the valence electrons, those outer shell electrons, for all of the atoms. Then you add an additional number, to add 1 for each negative charge. And if you have a positive charge, deduct 1. Well, let's look at an example. Here's NO3. What's the central atom? That's right, it's nitrogen. Okay, let's get the total number of electrons to be distributed for this. Let's start with the valence electrons for all of the atoms. Well, nitrogen has 5 valence electrons. What about oxygen? Oxygen has 6. And there are how many oxygens? There are 3, yeah. So oxygen has a total of 18. Anything else we should consider? Yeah, there's a negative charge. So we've got to add 1 for the negative charge. So what do you come up with? Well, 18 and 5 is 23, and 1 is 24. Do you get 24? Sure. So 24 is the number of electrons then to be distributed for the nitrate radical, or the nitrate polyatomic ion. Now let's look at H2SO4. What is the central atom? And the answer is sulfur. Now, I'll wait just a minute. You figure out how many electrons we're going to distribute for sulfurous acid. And did you come up with this? Did you get 26? 6 for sulfur, 6 for each of the 3 oxygens, and 2 for hydrogen? Sure. Well, look at this one. ICl2 with a negative charge. Figure it up. Did you come up with 22? Each of those halogens has 7 valence electrons. So 2 chlorines will have 14 and the iodine will be 7. That'll add to that, making 21, and then 1 for the negative charge. That's right. Got the idea? Rule 3 tells us to distribute electrons so that every atom has 8. Now, folks, we're just starting in this business of drawing Lewis structures, so we're going to use the octet concept right now, but understand that's going to expand as we go on, except hydrogen and a few others. Hydrogen, remember, can only have 2. All right, let's try the sulfite radical. What's central? Well, the central atom, yeah, is sulfur. And what's the total number of electrons that we have to deal with? Stop and figure it out. I'll wait for a minute and give you a chance to count the number of electrons we have to have. Did you get 26? Well, I'll show you where they go. Just remember, don't forget when we're counting these electrons that bonds count also. Okay, let's start with the central atom. There's sulfur. What's attached to sulfur? The answer is 3 oxygens. Here's one, here's another one, and here's a third one. Okay, now we've got the SO3 down. Let's get these electrons distributed. And I'm going to distribute them in pairs. I have 2 here, 2 here, and 2 here. Well, 2 here, 2 here, and 2 here. Let's see, how many is that? I've got some more. 2 here, 2 here, and 2 here. Did you figure out how many there were there? Yeah, let's see. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I need 2 more. How about here? There we go, 26 electrons. And we have the Lewis structure done for the SO3. Now, if you will notice, every element has 8 electrons. Yeah. Let's try this polyatomic ion, the NO2 -1, the nitrite. Now, what's your central atom? Sure, it's nitrogen. And how many electrons do you have? Well, let's see. You have 6 for each oxygen, and there are 2 of them. That's 12. You have 5 for nitrogen. There's 1 of them. It's going to give you 17. Oh, and you have a negative charge. So that's going to give you a total of 18 electrons. Now let's see how they're going to be distributed. I'm going to do them like this. And later on, when we get into molecular geometries, you will understand why I did them like this. Let's distribute those electrons. We have 2, 4, 6, plus we have 2 for that bond. That gives us 8. 10, 12, 14, plus 2 for that bond gives us 16. We have 2 more to go. Oh, how about here? That gives us our 18 electrons. How does that look? You say something's wrong? What's wrong here? Did you pick it up? Nitrogen has only 6 electrons. So what can we do? Well, let's have nitrogen and oxygen share 2 pairs of electrons. In other words, let's use a double bond. Yeah, just like this. So how about here? Yeah, we've got a double bond in there. Now everybody has access to 8. Well, that looks good. But that's only one way. What about this one? Now I hear you. You're saying they are the same. Are these the same? Think about using a heavy isotope for one of those oxygens. And then you will see that sometimes it would be double bonded. Then in one case it would be double bonded to the oxygen with a heavy isotope. That was the heavy isotope, and the other time it would not be. Actually, neither structure is actually correct. Both structures, though, contribute to what we have as a structure. The actual structure is a hybrid. It's a cross between both of those. You're familiar with hybrids. A donkey and a horse mate, and what do you get? You get a mule. Sure. The mule is the hybrid. Imagine a rapid resonance between these 2 structures, moving back and forth very rapidly, vibrating, flipping back and forth between the 2. And you get something that looks like this. Now, this is called the parent, and this is called a parent, and this is referred to as the hybrid offspring, or the hybrid of those parents. If more than one Lewis structure can be drawn, as in this case, it is probable that the real structure is a hybrid of those parents, and sometimes there are several of the parents. Are all parent structures reasonable? Well, not necessarily. How do we know when a parent structure is or is not reasonable? We use the concept of formal charge. This is a good place to stop, and we will take up formal charge in Lecture 2. A better way to teach and learn chemistry.